Yeah, thank you. All right. So today, we're rounding up what we have started about almost 5, 6 weeks. So it's supposed to be a 4 week series, but we missed, I think, 2 classes, 2 Saturdays. I hope you have gained some things so far. Like I've always said, the goal of these sessions is to build foundations, right? It's to help you build the right foundation that will enable you to build other things on it by yourself. Because if there's no foundation, whatever you build, it will be on shaky ground, right? So that has been the goal of the session. And we hopefully want to round this up today. I mean, unless if by consensus we are able to do another week. Today is going to be very packed, so much to do. And in the next class, I'm excited about it. And it's an area of particular interest to me. That's industrial communications, where we're going to talk about how we move data on the plant floor from the sensor up the ISA 95 hierarchy. Right. We'll talk about industrial networks. We'll talk about IP addressing. We'll talk about protocols. We'll have a look at Modbus protocol. We'll have a look at OPC UA. Those two will be our main focus. Then we'll look at Profinet. We'll gloss over foundation field bus and other other things. Right. So today I already shared the the workbook that we're going to walk through today. I've shared it. Confirm if you have it, give me a thumbs up. If you have that workbook, yeah. Okay. All right, great. So I already shared that. And there's a new section, Skill Catalyst platform, which I will just show you briefly before we continue. Can you see my screen? Is it clear?
No, sir, it's not clear. No.
Okay. I think it's the network. It's still trying to load. Let me change to this. Let's see if this will make a big difference. Let me just keep talking because of the time. So, at the top left, you will see a new tab, the new series, free series. So that is where we will be hosting subsequent. We've not populated it with the videos of the last 4 series, but at least we can use it for session 4, which is this one. But subsequently, this one will be hosting the link to the to the recording, and all the materials we use will be dropped in this session, in the tab, in the Skill Catalyst platform. So what we're doing with the Skill Catalyst is we have 3 broad offerings. One is this free webinar. Hmm. Right. The second is what we call the foundation class, right? Which is a paid class, right? I think there are some of the people on the foundation class here. And then the third is the platform itself, where you can take different courses, self-directed, all the simulations. So if you don't have an account there, I encourage you to sign up. You have more to gain than to lose by signing up. Right. So, I'm showing this to you because you will need to go back and look at the scenarios here. So, if you look at section 4 here and you click on watch session, right, this recording will be here. Um, will be, I mean, the link will be here, right? And then this is the session workbook, what you're using today. So if you don't have it, you can download it from this portion, right? And then if you click on this, it will take you to this PLC simulator where you can build this program, right? And then at the bottom is just very high level simulation of the process where you can look at certain scenarios. So for example, these are quick scenarios you can look at. These are your field inputs, and this is your panel. So these are the things you see physically on your panel. And then these are the memory bits and timers, what is happening inside the PLC. And then here, this is the process view, the tank itself. And then this is the ladder logic, the live scan. So you need to come back here and walk through this at your own leisure. So for the quick reset, you can reset everything, right? Then if you click on auto low level, it's not okay. Okay, so what is all of this? Also, okay, okay. I will, I will show this before we end. Sure. I will demonstrate this before we end. So, but you can click on these quick scenarios and you'll see how the field inputs changes, how it goes from off to on, LD, hold, and so on and so forth. And then you'll see the indicator on the pump, on the panel, and so on and so forth. All right. So the thing I couldn't include um in the in the workbook, the only thing is the drawing. I didn't have I didn't have the time to make the drawing. So that's the first thing we're going to do. We're going to sketch a drawing of the process, right? And then we'll take it from there. So I'll have to move from here to my iPad so that we can we can do the sketch on a notebook on my iPad. It's so slow. Mhm. Can you see my screen?
Yes, sir. Yes.
Okay, great. Okay. So the process, we are working on. So the process is a tank filling. I mean, the application we are working on is a tank filling application, right? So a pump fills a water storage tank, and then the PLC controls when the pump runs based on level switches, operator commands, and safety conditions. Right? The system supports two modes. There's the automatic and the manual mode. In the auto mode, the pump starts and stops based on level switches. And in the manual mode, the operator uses push buttons to start and stop the pump. If the tank reaches a dangerous level, the pump must stop and the fault must be raised. The pump must confirm it is running within 3 seconds of being commanded. If not, a fault is raised. So that is the process description, and it's in the workbook I shared with you. So let's quickly represent that as a diagram. A tank filling application is a very common process in the industry. In actual fact, even in the house, your home water tank is a very close example, right? The only thing we don't do at home is that we don't put a level sensor. We are not controlling it. We just we make so the tank in the house is being operated as an open loop process. You switch on your pump by a switch on the wall or something, and then you take your ear closer to the tank or the pipe, and then you hear the sound or you feel the vibration. You know that water is going into the tank. And then when the tank fills, nothing stops the pump. Your only indication is the overfilling. And then you suddenly hear splashes of water in the compound. And then, oh, the tank is filled. And then you go to switch it off. That is a classical case where we realize that automation does not bring any significant value. Why? Because maybe the 50 or 100 liters of water we're going to waste doesn't harm us because we have the borehole and water is in abundance. The water splashing on the floor is not hazardous. Maybe it's even good for the floor, right? So we don't bother with it. And then our need actually says that the tank should be full because NEPA might take light and we might not be able to pump. So it's best for us to have the tank to be filled maximally. So in that instance, we don't need the level transmitter. We don't need a controller. We don't need any feedback loop. We just keep it there, right? But flip that situation, and let's say we have a tank that is contributing maybe sulfuric acid to a particular process, and you have to fill that tank. Because of the fumes, you cannot fill the tank beyond 50% because you want to make sure that you have enough space for the fumes to stay. If you fill it beyond 50% and it goes to 70% or 80%, the fumes will be compressed, high pressure, and it can lead to a rupture. So in that instance, you need to implement a level sensor, a level transmitter, implement safety systems, implement protective systems to ensure that your process is safe. All right. So let's get into the sketch. So we have the tank. So this is the tank. All right. Let's close it like this. All right. And let's label this TK 101, which is a water storage tank.
Sir, we can't see your screen anymore.
Oh, you can see my screen.
Yes.
Oops.
I can see your screen, sir. I guess it's network.
Oh, okay. And can anyone other person see my screen?
Yeah, we can see it, sir.
We can't see it too.
Ah,
I can't see it either.
okay.
It is
So
black.
you need to probably okay, presently it's blank. How about now?
Still okay.
Yes, we can.
Yes, we can see it now.
Okay, great. All right. So so that is the tank, right? So we have a tank. We have our controller, or let's say so we have, let's say this is the analog input card, right? Or let's just call it the PLC, so that we don't have to distinguish between input and output, right? So let's say this is the PLC, right? The controller, right? So that is the PLC. We have a pump, right? So we have a pump. Let's say we have a
We
pump.
can't see the screen again.
Are you kidding me? What's happening?
We can still see it too.
I can see your screen. I guess it's his network. It will be his network. I see
Okay.
it clearly.
Okay, so yeah, check your network then.
Okay, now it's okay.
Okay.
It's okay now.
Maybe your network needs deliverance. Yeah. Okay. Let's see from okay, let me yeah. Okay. So we have that so this is the inlet into the tank, right? At this inlet, we have a flow transmitter, right? A flow transmitter, right? This flow transmitter is connected to a valve, right? Let's call this CV, let's say CV-101, right? And then it goes into a pump, right? For you guys in the foundations class, I mean, I'm using what's it called now? I'm using the normal standard, the PID symbols, right? So you should take note of it. So this is the pump, and then you have the motor. So when we talk about a pump, the pump comes in two configurations. You have the motor that drives the pump, and then you have the impeller, right? So you have that motor, right? And then that connects, let's say, to the mains. Yeah, right. That connects. to the mains, right? Now on the tank, based on, you can reconcile this. I want to move fast, right? You can reconcile this with the narrative in the workbook you have, right? So on the tank, we have this, right? I'll label this now. We have this, and then have this, and this is the LSHH. This LSH, and then you have LSL. Right? You can tell me what's the meaning of LS?
I think it's level switch.
Yeah. So level switch. What about HH? H and L.
I, and the other one is I.
Low. Excellent. 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 All right. So labeling it further. So this is the II switch. Is for the trip. If the sulfuric acid gets to this limit, bring the system to a safe state. So that is the sentinel. That is what is going to instruct the controller on what to do. Immediately, the level in this tank gets, once LS becomes true, the system will trip, right? It will not allow the system to, it will not allow the tank to continue to fill, right? So the tag will be HH LS, right? And then whatever you want to put it. So let's say, okay, let's just leave that open. All right, HHLS. Let's say 101 or whatever, right? For the LS, so that would be HLS, right? And the function of this is pump stop, right? And then this is the low LS, which is pump start. And it's also used by auto. Is this making sense?
Yes, sir. It's making sense.
Yes, sir, it's making
Okay.
sense.
All right. So on this tank, right? So let's say that this is the level of fluid in the tank presently, right? So just to represent that. Right. Now, and this is the low level alarm that indicates that the tank is low. The proper design demands that you implement something at the base of this tank in case you want to evacuate everything in this tank. So you need to have a drain somewhere here, right? So that's like a drain valve, your XV 10, let's say 101 or whatever. Okay, we have an XV here also, sorry. So let's say XV 101, and this is 2. Right? So that serves as a drain. So that's a drain valve. So that's a very good process design method. So now, so those are the physical things, right, that we need to factor in our sketch. Now, the next thing is the signal, right? Recall that we have a panel we use this. So we have our panel somewhere here. That is a physical panel, you know. The process demands that we should be able to operate this tank system either in auto or manually. So somewhere here, okay, already used. So we need our start PB, right? Here. This. So let's represent it well. So let's so that is a panel, right? And then we have this, which is our start PB. We have this, which is a stop PB. And then we have this, which will be the reset PB, right? So this is start underscore PB, stop underscore PB, and then reset underscore PB. And then of course we have our indicators, right? For when it is running, or when you have a fault. So when it is, so this is run. Or when you have a fault, right? So now we now need to wire the signals, right? There is an e-stop. Okay, so let me use this also. Okay, it can be proportional, but let's just take it like that. Okay, let me put it outside here. So there is an e-stop, right? What's an e-stop?
Emergency stop.
Emergency stop.
Okay.
Stop button. Stop button, sir.
Okay. How is an e-stop different from an ESD? What's the difference?
No, I didn't get the question.
There is e-stop. There is SD. So I said, what is e-stop? You said it is emergency stop, right? Then what is, okay, maybe we go further. What is ESD?
Emergency shutdown.
Please shut down button. Please shut down.
Okay, emergency shutdown.
Yes.
So what is the difference between the two?
The ESD is the valve that actually when the command is actually energized, then then you stop, allowing flow into the system. Why the e-stop is to stop the panel, as in the motor from running. That's from my understanding, sir.
Sorry, come again, please. Come again.
The ESD is actually has to do with the valve position of actually, if you have any fault alarm, you should actually start to stop stop the valve from actually allowing anything to pass through, the process to pass through. Why the ES stop is the emergency stop is to actually deal with the panel, as the panel on the motor, not to allow any current to pass through. That's from my own understanding, sir.
Okay, so if I hear you right, emergency ESD is for valves, e-stop is for panels.
Yes, sir.
Okay. Any other opinion?
Good morning,
I
everyone.
think
The condition, the e-stop initiates the ESD command.
Okay. So you just told us a relation. What the difference?
for me, I don't know what the emergency stop means. When you press the emergency stop, it means all parts should return back to basic position. Whether from the cut off the lights, cut off the air, cut off the valves, everything stops immediately.
Okay. Emergency shutdown stops the whole plant, system of plant. Okay. Abiola.
Yeah, good morning, sir.
Yeah.
I believe emergency shutdown is when the system is on auto. When the system is on auto, it trips the plant. It's mainly to trip the plant when the plant is on auto. While emergency stop is for when you operate from the panel. That's when it's on manual. You operate it from the panel. You operate the emergency button from the panel. Thank you.
Very, very, very interesting. Very interesting. I'll come back to that. I'll come back to that. No, don't clap yet. Don't clap yet. Don't clap yet. But it's a very interesting answer, right? You related it to auto and manual. That is the only point where I disagree with your answer, right? But Abiola, let's hear you.
Hello, sir.
Yeah, hello.
Yeah, you called me.
Yes, you raised it.
No, I have spoken already.
All right, right. John Elliott.
All right, sir. Good morning, sir.
Good morning.
So, to my own understanding, emergency stop now. It stops a particular machine. Let's say we are a plant is running a line, so that emergency stop stops a particular machine. Why emergency shutdown shuts the whole line down?
Okay. 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 Great. So, yeah. Okay. So, thank you. So, the interesting answer, the gentleman that spoke about auto and manual. I mean, it's so I never thought of it that way. It sounds right, but it's not right. So, first need to understand. E-stop, yeah, sometimes is associated with good use, right? A panel. You have your e-stop button on it. ESD is a product safety system. So it is called emergency shutdown system. And that is clue. It is a system, so it governs a number of units. X amount of units make up a system, right? So e-stop, you wire it most of the time into a PLC input, or output card, right? So, I mean, you wire it into whether input or output, right? ESD, oftentimes you don't wire it into a PLC. So, where do we use ESD? Where do we activate ESD? What kind of control activates ESD?
DCS.
I thought
Yes,
at the main power supply.
yes. Power, of course, it will use the ESD will use power. Yes, power in some form. Some ESD don't use power. I'll tell you. I will explain that. So, your shutdown system, you most of the time you tie it to in the manufacturing plant, you tie it to a safety relay circuit, or to what we call your SIL, your safety PLC. Are you following? So you tie your e-stop, right, into your normal PLC, right? But your emergency, so the first thing is emergency shutdown system, right? It governs a number of units. It's not localized into a panel, right? So if you have one tank, or let's say if you have 3 tanks working together, maybe they are interconnected in a process environment, right? It is ESD that will act as a safety guard for that system. But on the panel, for each unit, for each tank, you have an e-stop, where if you press the e-stop, you shut down the operation of that tank. But the ESD will shut down all the 3 tanks working together. And then I now say that your e-stop, you oftentimes wire it into your PLC inputs, right? And you're just watching whether it is LD or otherwise, right? But your ESD, you wire it into a dedicated safety relay, or you use a safety PLC or SIL rated PLC. Does it make sense?
Please come again, sir.
Okay. ESD. So the controversy is e-stop, ESD. The way we organize the plant. So we can have, in this instance now, we have tank TK, right? Let's have pump 202, right? Then what is happening here? Maybe the upstream tank that is supplying fluid into this our tank is another tank TK102, right? So each of these guys will have an e-stop and local control. Doesn't have a panel that is controlling them, so they will have an e-stop. It means whereby the shutdown individual units, right? Now, for ESD, so if we have, so this is tank 101. This pump example, this pump here might not be 2, right? So let me put that. So this is 102. Here we have a compressor where, right? All of them working together, right? There will be one ESD connection, one ESD, right? But this one ESD, so if this environment is big, I mean, let's say this is the area of the environment, and this system is working with this system, is working with this system, and all of them are somehow connected like this, right? Now, we locate your ESD button. So it is one circuit, right? But you have, let's say, ESD station here. You have one ESD station here. You have another ESD station here. You have an ESD here, right? You have an ESD station here. The goal is that if I press this ESD button, right? I mean, so that's why we call it a circuit, right? All of these are connected. So the goal is that anyone that I activate here, boom, will trip the whole of this system. It will bring them to a safe state. Why do we replicate this thing across? The plant is big geographically. If something I want to, yes, okay, so it is expanding now. Yeah. I'm conscious taking me out of my goal this morning, but it's worth the explanation, I think. So if something is happening, right, and there is this human at the end of the plants, right, I want to ensure that when one activate this button and then it runs away, right, so that it can to safety, right, this button will cause a trip of all the processes here. Do you understand? Also, safety PLC, CPLC, or your safety relay that are watching for conditions can also initiate ESD for the whole system. Does it make sense now?
Yes.
So much, so much sense,
So,
so much sense.
okay, excellent. So it's a whole lot of things in the process plant. So now we have SD. If we begin to expand it, we have what we call OSD, right? But I won't go into all of those so that we don't start another lecture. Let me just check for the sake of the recording. So, okay. Let me do this. Don't want to clean it. All right. So, so here's the anyway. I think it's worth it, right? The explanation was worth it.
Yes.
Okay, great. So the next thing is for us to wire the signal, right? So we have our e-stop, right? So we have our e-stop, right? What are the things that we want to stop? Right. So firstly, we wire this. How do we okay, let's use green. So this e-stop, we wire it into the PLC, right? Then this motor, so now my drawing will be rough, right? So we wire the e-stop into the PLC, right? Now, the motor here, we wire it here, right? Is it making sense? Okay. Then the motor, so that's color. So motor, the same motor. to the PLC, right? Have connection from so the PLC. So I won't see any connection. What does connect? Okay, I think we are okay now. So, do you have understanding of the process now, or is there a question on this? So that we go into, so that we move to the work, and then we to the workbook. So,
I think the network is really affecting me for my own.
Sorry, say that again.
I think the network is affecting me. I don't know if it's for my own end or for your end, but I can barely hear you.
Not only on your, it's breaking.
Oh, it's breaking.
Yes, but I can barely hear you. It's just breaking.
Oh, okay.
Like,
Okay, let me change this network.
Thank you, sir.
Okay, so what I'm saying is, this sketch, does it give you an understanding of the process that you're trying to walk through now? So I want us to move to the workbook and quickly walk through it. Can you hear me clearly? Give me a thumbs up if you can hear me.
Yes. Yes, sir. Yes.
Okay. 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 All right. All right. So I guess I'll stop sharing this. Let me try to open the workbook. Oh, sorry. Let me open the workbook. Okay. Confirm you can see my screen.
Confirm, sir.
Excellent. Excellent.
Confirmed.
Yeah. So this is the workbook we want to go through, right? So we'll do as much as we can before we shut down the class, and we probably will need to discuss if we want to take one more week or we move to the next item. All right. So this is the process I just illustrated. That is the process description, right? I read it out earlier, right? And then these are the activities. Every professional automation engineer follows the same sequence when writing a PLC program, right? So my goal, right? My goal is for us to demonstrate the right professionality when dealing with control systems, right? We need to raise our level of competency within our ecosystem. We need to, at some point, I want to see Nigerians being exported, Nigerian manpower being exported to support and build process systems globally, right? And to achieve that, we need to be able to think structurally and methodically. So that's why I always say that your goal as an automation engineer or a control systems engineer is not to just be able to write a PLC program. Anybody can write a PLC. Anybody can understand all the instructions. The thinking behind it, the design, that is what should be your goal. In actual fact, you can do the design, set up, define the I/O, write the control narrative, build the tag table, and then give it to a technician to do the writing and do the implementation. And then you test and then you commission. Right. So that is the goal here. So that's why it is important that if you really care about it, you go through these steps. It's a disciplined step, and I took pains to prepare this workbook, right? So the activity number 1, these are the questions we now need to ask ourselves, right? Which 2 steps must always be completed before you open the PLC programming software, right? Before you open any PLC programming software, which 2 steps must be completed? So the structure of this workbook is that you have the activity and then you put in your answer. You think about it, you put in your answer. And then, so this activity 2.1, and then these are the answers. List 3, list 2. I mean, just like the comprehension we did in secondary school, and so on and so forth, right? So can we begin to answer this? Based on the drawing we made, I mean, based on your process understanding, right? Now you want to develop a program, an automation system, right? For that process, right? So what are the things you need to do before you even open your PLC programming software?
So do you didn't answer or what?
Yes, I'm asking you. I'm the examiner now.
Step 1 and step 2, we done.
Okay.
And then you need to know your inputs and outputs, and
Okay.
you need to know what the system should do. Like that's number 2. You should know what the system should do so that you get what the results you want. So step 1 and step 2 should be done first.
So tell me, what is a controlled narrative?
Control is telling it's like an explanation of what should be done. I should get at the end. What should you get at the end? That's what I think it should be.
No. You said you should get at the end. You are talking about the results.
Like what the system should do.
Yeah, it's okay. Any other person?
Okay, yes, sir. Can I come in now with my own view?
Yes, please.
Okay, so I might actually don't actually be correct, but I think I will.
No. You know, I mean, we are all learning together.
Okay, sir. I will consider step 1 and step 3 very important first.
Okay.
The reason why I will consider this. The reason why we consider 1 and 3 is because on having understanding the input and outputs of the PLC as in the narrative actually, then a tag must be I must assign a tag to all the devices and all the input and output tags I'm going to deal with. So if I'm able to have these tags being put in place, then I will know where to wire my input and output signal to. So that is my own take, sir.
Okay, how will you know how to do the wiring?
Okay,
you have defined your input and output, right? You've built your tag table. right? So what will guide you to do your wiring and your programming?
So that is it, number 2, the narrative.
Yeah. So because you said because you mentioned 1 and 3. All right, John. Then Philip after.
Okay, so good morning, sir. So for me, the first and second step will be the number 1 and 2. We'll define the IO, and steps 2 we'll write the control narrative as you've done. You can even include the drawing to know how the system wants to work, the things we need to do, how the wiring will go, and all of that. So step 1 and 2 has to be done before going to step 3.
Okay, great. Philip.
Okay, good morning, sir.
Yeah, good morning.
So I'll say I'm in support of step 1 and 2. I was almost dropping my hand before you called me.
Okay, all right. So,
Yes, sir.
Yeah, step 1 and 2. You need to understand your input and outputs. Yeah, Achanya Peter.
Okay, sir. Good morning, sir.
Good morning.
Yeah, my own understanding about it, just like everybody has said, we'll take step 1 and step 2. You asked the question about what control narrative means. So my
Yeah.
own understanding, the control narrative has to do with, just like one person said about how the wiring and everything will go. You give the steps pertaining to each wiring and the guidelines, and also how it works, more like a manual to how to define the IO. That's just my understanding, sir.
Okay, excellent. Excellent. Something just occurred to me. I'm not sure. I'm not sure myself. So, is anybody Emmanuel? Yeah, Etafo.
Okay, yes. Good
Oga, how you
morning.
doing now?
Yeah, I know. Good morning, all. Okay, so for me, I will say step 1 and 2. But step 2 first, we have to understand, okay, what's the control narrative, the control philosophy, the cause and effects, understand the engineering part. Then before you now think about defining the input and output, your IO list, where the analog, where the digital input and output are supposed to be placed. So step 2, step 1 should be the sequence here.
Okay. I agree with you. So we're not discussing it in terms of priority.
Okay.
The fact, I mean, but you are right? You need to have your control narrative, right? There are some. So I was going to ask a question, right? Aziz, I'll come to you shortly, right? I was going to ask a question. What is the difference between a control narrative and a control philosophy, right? I don't think I can even define it myself, so I'll need to check that online, right? Aziz, quickly, while I check this online, you can quickly make a comment.
Okay. Good morning, everyone. I just want to comment on the control narrative thing. Most people are mentioning the wiring and all that. I don't think it's explicitly talk about the wiring. It's just like it's mostly like the connection, the interlocks, strip sequence, and description of the process. That's like majorly what a control narrative like entails. So that's just the comment.
Yes, and that's actually the thought that came to my mind. Why I want to differentiate. Can you see my screen?
Yes, sir. We can see the screen. I can see your screen.
Okay. That so you can see I'm displaying control philosophy and control narrative.
So we can only
right?
see the workbook.
You can just see only the workbook.
Okay. Sorry.
Workbook.
Uh, um, So, Aziz, thank you for bringing that to for surfacing that. So, control narrative is not just about connection, right? Part of the things you need to identify earlier on is, for example, how do your auto and manual, right? You want to be able to operate that tank in auto mode or manual mode. That's part of your narrative. It has nothing to do with physical connection between components, but you need to specify that, right? So, control philosophy. So, I just wanted us to look at the difference between control philosophy and control narrative. So, the philosophy establishes the big picture of the process. It defines what the plant is trying to achieve safely and reliably, right? Can you see my screen? Can you see the definition on the screen?
Yes, sir.
Yes,
Okay,
yes.
excellent. While the control narrative translates the philosophy into executable engineering intent, it details exactly what the automation does rather than just what a human should do, right? And then the content provides specific conditional logic, dictates field instrument parameters, pump/valve states, sequence timing, interlocks, and cause and effect mechanisms. And it is used directly by programmers to write the PLC code and by instrumentation teams during FAT, right? So, I read a lot on this automation forum, so I recommend it. I highly recommend it. So we can see that now, right? The difference in the control. What's this? Hello, can you? Okay, I'm still logged in. So we can see the difference in the. So we can see the difference in the control narrative and the control philosophy. Yes, Aziz, you wanted to say something?
No. I forgot to drop my hands. Sorry.
Okay. Thank you very much. All right. So, those are the two steps you can take, right? You can choose to include control philosophy in this action, right? And just put it there. The goal here is that you have the understanding. Nobody's grading this. Nobody's marking this. The goal is that you have the understanding. All right. So now getting into the process, what is being controlled?
If the pump is being controlled, the pump, the valves.
Okay, level. Okay.
So the process is being controlled.
Yes, now, of course, the process is being controlled. So someone mentioned the level.
Tank, sir.
Level.
No.
The
Who says tank? Are we controlling the tank? We are not even touching the tank.
The flow rate
level.
You said?
So the pump, the control valves, and then the level.
So we're I mean, we're using the pump, right? What the level is doing is the level is telling us whether the action of the pump is enough or it's overdoing it. If you recall from the sketch, if you recall from the sketch, okay, there's a sketch. So if you recall from the sketch, all the level instruments we have here, they are switches. So we're not using level for control, right? So the one at the bottom here is LS, low level switch for the low level. And what it is helping us to know is when to start refilling the tank, so that when the tank goes low, we start refilling. And if the process is on auto, it automatically, the system automatically knows when to start the pump, right? The second one, LSH, is the high level switch, right? To know when the pump should stop. And then the third one, LSHH, II, that is the trip alarm, excuse me, to know when to shut everything and bring the system to a safe condition. So it is the pump that we are actually controlling, right? It's a pump. It is filling water. We are not even using the flow transmitter. I mean, the flow transmitter maybe is just providing data to some HMI, right? Just to tell us the quantity of fluid in the tank. Are we agreed on that?
Exactly, 100%. You're right.
Okay. Okay, thank you. So we are controlling the pump motor. Now, what is filling the tank? You know, I mentioned that this arrangement we have here is a combination of a pump and a motor. A motor drives a pump, right? So when you switch on the motor, it drives the impeller, and that impeller pushes fluid, right? So the signal coming from your PLC is directed at the motor. It is the motor we're switching on off that we are modulating, right? We don't care. So the need of different processes are unique. We don't care what happens at this level in this tank. We don't care what happens. Sorry, apologies. We care what happens at that level. That's my pencil. So between this level and this level, as in just before the high level and the low level, we don't care the we don't care the level of water. It's not in our control philosophy. We don't care to know, right? We only care to know when we are at this point and at this point. That's where we care to know. At this point, it is out of our hand. Whether we like it or not, the system will trip. Are you following? So the pump will continue to fill. As in, okay, let's assume that the tank is empty. So if the tank is presently drained, let's say this drain valve is opened and there is no fluid in this tank. So at the initial point, there is no fluid in that tank, right? And then we activated the pump, the motor. The motor drives the pump, and then fluid started coming in. Did someone, yeah, Fedosa? You want to say something? All right. When you're ready, just open your mic and speak, Fedosa. All right. So the tank was empty, and then it begins to fill with fluid. Poo, 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 poo. You will see that when it begins to fill, this low-level alarm will be there because we already drained this pump, this tank rather. Then as it begins to fill, once the water gets to this level switch, and that is why this is a switch, not a transmitter. A switch is not the same thing as a transmitter. A level switch only have two states, on or off. A level transmitter has states between 0 and 100%. It can take any state in between 1%, 2%, 3%, 10%, 50%, up to 100%. So you need to note that distinction, right? So when the level get to this point, this level switch, the state will change. It will stop seeing low level, right? And then the tank continues to fill, right? And then it gets to this point. This LS level switch again, for the I side, the state will change, and then it will register I alarm on the HMI. I alarm will be registered there. If for some reason the operator, if for some reason this motor did not stop and the operator couldn't bring this motor to stop, if it didn't stop automatically and the operator couldn't bring it to stop, and then it continues going up, at this point, this is a trip alarm. It does not require the operator input. It's going to trip the system. It will force this motor to stop so that we don't have a spill. Are you following?
Yes, sir.
Yes, yes,
Yeah.
So excellent.
yes.
So that is why it is the motor for this process. I mean, we can choose, if you are the engineer designing this process, you can choose to say that I don't want to control via motor. I want my control to be tied to my level, right? So then you can use your level transmitter or even this level switch, right, as your means of control. That is why your control philosophy and your narratives are very important. That is the paradigm with which you are going to look at the system. Do you understand?
Yes, sir.
All right. So our time is gone. Let me just take, if you don't mind, let me just take 10 minutes to wrap this off. Okay. I actually have a meeting by 9, but let me take, okay. Okay, Edosa didn't say anything. So Tion Charles.
Hello, good morning.
Good morning, sir.
Hello. Yeah. So what is the difference between you level transmitter and level switch? I think they are performing the same function. I think. Is it by application? Hello?
So there is a transmitter. This is my cheap pen. So there's a transmitter. There's a switch. So instrument. So for level, So we have level transmitter and we have level switch. Okay, let me do it this way. So for level, the transmitter most of the time will operate on 4 to 20 milliamp, right? The switch will either be 0 or 1, on or off. Sorry, my pen is, the battery is flat, right? It will be on or off, right? So the same thing if you have a pressure instrument, 4 to 20. This can only take 0 or 1, on or off. That's the two status. So if we say that the resolution of your level, if your level transmitter is rated 0 to 100 PSI, this level transmitter can, PSI for level. And you people didn't correct me. 0 to 1000. 0 to
column. Yeah.
Let's just use the centimeters, right? So this level can tell you that the water is at level 0, level 1, level 2, level 3, level 10, 50, 80, 100. But a level switch will only tell you that there is fluid air, true, or there is no fluid, false. It's one of these two. So a switch, just like the switch in your room for your light, you can only turn the light on or off. But if you have a dimmer switch will reduce the intensity of the light. It will be a bit on, more on, very bright, and so on and so forth. Does that make sense to you?
Yes, sir.
All right.
Yes.
All right. So that's the difference between the two, right? So now, what stops filling tank? So if the fluid gets to this high level, what mechanism stops it? Or what equipment stops it?
Sir, come again. What we get to what level, sir? Please come again.
So if the fluid, we are filling this fluid in this tank, and it is going up, at high level, once this LS equals to true, right, we know that it has gotten to the level. So this is like the set point, right? So how do we stop the fluid from increasing, from going beyond this level? What mechanism?
I think
What
the pump
equipment?
stop. The pump.
We use the stop button.
The pump will stop.
Okay, the pump, the pump is dummy. The pump needs to be instructed. How does the pump knows when to stop?
I think there's a switch there.
I think if we are going logical, if we are using ladder, once the thing got to
level switch.
Don't overthink this. Don't waiting with that song. Overthinking, no, this a problem. Better life now.
I think
the level switch high.
So the level switch.
I think
once it gets
yeah.
And
the level switch is there. Level switch, the ones switch level, then it will send a signal and click.
Hold on, bros. What is the function of the level switch?
Hello.
the function of the level switch is just to
open the circuit.
Open and close.
The function of the level switch is to tell us that there is water at this level.
The level, okay.
It doesn't do anything beyond that. It doesn't switch off. It doesn't stop the pump. It only indicates that, okay, there is water at this level. So what mechanism? So when there is water at that level, what mechanism will stop the pump from pumping additional water into the tank or additional fluid? You know this thing, though. You are just overthinking.
The control what?
The controller.
It's the controller.
It is the controller. So you can use your stop PB if you are operating in manual, but the assumption here is we are operating in auto. So that is where your logic comes in, and you say that if ls underscore h equals to true, then m equals to 0. Do you understand that logic? Because
yes,
M is the only equipment connected to the PLC, right? So, okay, just hold on then. Hold on, Salome, just hold on without question. Let me finish this intuition, right? So M is the only equipment connected to the PLC. Now, M drives the motor. M drives the pump. The pump pushes water into the tank. The tank, LS detects the level of the tank, right? And then this logic connects M and LS to achieve what we want. And that is why I always say that this drawing, I mean, people that have been in this class will know that I love this drawing. Sensor, controller, and actuator. Right. This drawing will model any control system. Right. So it is in this controller that you have this logic. You've written this logic into the controller. The sensor senses this process, right? And then delivers the results to this controller, right? And then the controller sends an actuation signal to the motor to stop because we have attained our goal. So let's Sion ask a question and then Achanya, and then we'll take Salome. Sion?
Yes, you have answered my question. Thank you. You have answered my question.
Then Achanya Peter.
Okay, thank you very much, sir. I just want to get a clear understanding about this. While I was doing my internship, that's about pressure transmitter and level transmitter. My instructor told me that the two are the same actually, but the way we give the difference is where they are being inserted.
Hold on.
Okay.
Just hold on.
Okay,
you
sir.
said pressure transmitter and level transmitter. Is that correct?
Yes, sir. Yes, sir.
The two are not the same thing. No?
Okay. Okay.
The reason,
okay.
I mean, pressure is a parameter, level is another parameter.
Okay.
They do different function. One measures level, the other measures
pressure.
Pressure. So you probably maybe you didn't state your premise properly, or you didn't get what your instructor was trying to pass across. But
Okay.
level and pressure are not the same
Not the
fundamentally
same.
by
Okay.
physics, by chemistry, by any measure.
All right, sir. But sir,
Yeah.
I want to actually say something pertaining to the two of them.
Okay.
The that's talking about the areas where they are being inserted. I think
Right.
level transmitters are inserted in tanks, while pressure transmitters are inserted in pipes, or how should I call it, like, yeah, pipes. I don't know whether you understand what I'm saying, because
I
anytime
understand.
I refer to the level, like it says the two kind of like want to function in the same way, like level 2 sometimes measures the pressure that comes into the tank. So, but from the explanation you're giving now, it is clear to me now that level is just strictly on level and it doesn't have anything to do with pressure. If I really understood what you said, sir.
Yeah, I'll quickly show you this. So you can use both level and pressure anywhere. So look at this example of, let's look at this tank. Can you see my screen?
Yeah, I can.
So this is a P&ID example of hot water storage tank, right?
Yes, sir.
So if we quickly look at this, so this is the, okay, let me do something so that I can annotate it. All right. So if you look, this is the hot water inlet, right? This is nitrogen inlet, right? Then this is a valve that controls the flow of nitrogen, right? And then this is PIC, right? This is a pressure loop, right? This is level.
Okay, sir.
Right, that's a level gauge, level transmitter, level indicator.
Yes, sir.
Right. So you can see that this is it, and then this is temperature transmitter.
Transmitter. Yeah.
And this is the controller.
Yeah.
Right. And then this is the
Yes,
heating pad, and you can see the signals. Right. Now, you can see that this is a tank.
Yes.
And on this tank, we have level and we have pressure.
Pressure. Yes, I see, sir.
Right. So, I mean, in installation, for pressure, by its nature, you only need 1 point, right? You insert at a point, whether on the side or at the top. But for level, oftentimes, for level transmitters now, you install at 2 points. So you have a flange here, and then you mount your instruments here, right?
Yes.
And there are different, see, this is a whole I mean, probably five days training. There are different types of level measurement technology. So there is a radar one that you install at the top, and then it shoots radar down to the level of the water, and then the radar comes in, and then the time of flight is estimated to give the level. There is the other one that uses differential pressure to estimate level, right? So the point I'm making is that there is no single there is no, how will I say that now? There's no law that says that you can only install one on a pipeline or another on a tank. Yeah, so that's why you are the engineer. You are the one, I mean, at least you are the god of the machine. So you are the one that is creating the machine and giving it life and intelligence, right? So you make that decision on how to use it. If I have a pipeline, normally I don't want to estimate the I mean, I don't need to know the level of fluid in a pipeline. But if there is a process requirement for me to know, then I can design an instrument, a level instrument, to monitor the instantaneous height, level rather, of the fluid in that pipeline.
Yes,
Right?
sir.
So that's what makes me an engineer. Bring me the problem, and then I provide the solution in an economically viable way. Yeah. Okay. So
Thank you very much, sir. Thank you.
yeah, thank you. Peter, before you talk, I don't want Salome to be upset with me. Salome, take your question, and then it should be ladies first, self, even before. So ladies first before Etafo and Peter.
Sorry, sir.
Sir,
I've already
good
spoken. No, I
evening,
think
sir.
it's Emmanuel that is raising up his hand again.
Oh, okay, Emmanuel. Okay. So Salome before Emmanuel.
Thank you, sir. Good morning, sir. Sorry, this question, you don't necessarily have to answer it in this class. But I
Okay.
wanted to make a comment about the other person's question on the transmitter. So
Okay.
in my plant, there's this immersing differential pressure transmitter that depending on how you configure it, you can use it to measure either level, flow, or pressure because of the mathematical relationship. So I am thinking maybe that's what it's talking about. Yes, I just
Okay.
wanted to comment on that. Yes.
Okay. Thank you very much. Yeah. So those class of instruments, we call them multivariable transmitter. Right. So those kind of instruments, we call them multivariable transmitter, whereby you install one and then you have different parameters. So multivariable transmitters are advanced industrial instruments that simultaneously measure differential pressure, absolute static pressure, and process temperature within a single device. And we use it a lot in flow measurements, gas flow, fluid flow, and so on and so forth. So thank you for bringing that to our notice here. All right, Emmanuel. So let's take your question, and then I guess we can call it a day.
Okay, yes. So, now I understand the concept of the level transmitter and level switch. But for this your setup, so you are saying it's wired to the PLC. So is it to the ESSDS? It should be to the ESSDS, right?
Are you talking about the level switch?
Yes, the level switch and the level transmitters.
Okay.
The level switch, sorry, no, the level switch, not the transmitter. Because transmitter should be seen on the DCM.
Exactly. So first, there is no transmitter in this process.
Okay.
Right. Everything, all these three devices are switches, right?
Okay.
Yeah, this one, I will need to deface this drawing now. This LS low level switch is why it is being reported. Okay, no, not even that way. So this low level switch is connected to this PLC. Of course, you know that the PLC through the comms, right, is linked to the HMI, and then you do your tagging and whatever. So on the HMI, you will see the LS, the low level switch signal. The same thing, right? So here you will see the HLS, right? Now, this trip first goes to this equipment. In implementation now, right? The trip will go to this PLC. Tell me, is it going to be an input or an output?
It's an input.
Why is it an input?
It's an input.
It's an input
because
Now fight. What? Why is it an input? That's the question I asked now. Oh yeah, tell me. Oh yeah, tell me, why is it an input?
I think it's because the PLC will take an action based on that value that it's getting.
So this is going to be wired into the input card, right?
Yeah, yes, sir.
Digital input or analog input?
Digital.
Digital input, because it's a switch.
Yes.
It's 1 or 0, right? So this goes into an input, and then there will be a logic block inside that, which is your program. So let's call it the shutdown. No, let's call it the trip logic. So there's a trip. So once the input receives this, right, inside the PLC, this trip logic becomes true. And the output goes into what? Into a DO card, right? And then this DO card comes to this motor to shut it down. Do you understand?
Yes, I do.
So that is for the trip, right? Now, if you are implementing this unit as part of a larger ESD system, right? I mean, your cause and effect matrix and all of those things, you will have done all those analysis, because you might determine that if you don't shut down this system, or maybe shutting down this system will cause unsafe conditions in other upstream or downstream units, then you will take this strip, wire it into another circuit. Sorry, just follow the diagram is rough now. So
yes, I understand.
So let's say this is a safety PLC, right? So you take this trip, you wire it here, you take the trip from another process, let's call it trip 2, you wire it here, you take the trip 3 from another system, you wire it here, and then you have your ESD logic. Are you following? So that all the units connected together, if you trip this, and based on your cause and effect, you know that tripping this is going to cause an unsafe condition for the downstream or upstream process, then your ESD will now take over. It will now shut down everything so that there will be no unsafe condition in the plant.
Okay, this is clear now. Thank you.
Okay, excellent. So I mean, we've not even finished analyzing this simple process. So just think about the kind of thinking, the kind of consideration that goes into, let's say, a boiler process in Nestle, or an oil and gas facility, a flow station that is handling hazardous location across board. Just think about that. And then you'll begin to see the amount of responsibility that rests on the shoulder of the control systems engineer. So, guys, I'm 25 minutes late for my next meeting. They've been messaging me. So the question we now need to answer now is that we have started this, Where's the so we have started this now. We've only done we've only sorted page 2. In fact, we didn't finish page 2 because we've only discussed what is being controlled, what fills the tank, and what stops filling the tank. We need to look at the fault scenarios, 3 fault scenarios. We need to list 2 operator actions and then the PLC restrictions. All right. So the question is, should we, will you go and continue this on your own, or should we progress again on this next Saturday?
Next Saturday, let's progress again.
I'll continue.
So
you can drop the
So I
material
think
for us
it's
to go
better
through.
to continue. Then we move on to the next, maybe industrial networking next week.
Okay. So you have the material already. The material is in the WhatsApp group, so you can pick it up there. If you are not on the WhatsApp group, you should get on there. That's where we share information. I mean, I can't upload these documents onto LinkedIn, so it's easier to share information, or you go to the Skill Catalyst platform and download the material. So what we will do is we'll drop a survey, a poll on the WhatsApp group on whether to continue this or we move to industrial networks next week. So thank you very much, guys, once again for your time. It's been very interesting. I also have learned. I'm learning. You know, there are some things that you assume that you know, and then people ask you a question, and it jogs your knowledge, and you say, "Okay, am I really sure of this?" So when you see me running to the browser, it's because I'm trying to clarify whether I really have the understanding or not. So this has been a symbiotic relationship. We are both learning. And thank you for the claps. So have a beautiful weekend. Further questions, you can drop it on the chat group, and I will take it from there again. So what's it called now? The recording will be dropped on the group. The recording will be dropped. The link to the recording will be dropped on the Skill Catalyst platform. And a big change is coming to Skill Catalyst. The platform is less than 2 months. The registered persons is approaching 500. So people are really accepting it. I know the UI UX is not fantastic. So we are trying to make a change. We are rearranging how things are done. We are putting a link for videos. So just keep your eyes peeled for the changes. I think we'll begin to implement the change by the end of this month. And for those of you that have not registered, you have your founders code. The first 300 persons that are registered on the site, they have a founders discount code that gives them 50% on subscription for the next 12 months. The code is going to expire, I think, in 2 days' time, on the 15th. So you better use it. If you want it, you can use it. Otherwise, you'll pay the full amount when you need it. So, and of course, there's discounts for students, very discounted for students. If you're a student, you can discount it. And the other thing I'm going to add is the foundation class
is very, very important. The guys in the foundation class will tell you the level of things you are doing in that class, even though we call it foundation, but it's beyond foundation, right? So it's a class you should consider joining, right? It deals with, we discuss process, we discuss instrumentation, we discuss valves as a topic, we discuss PLCs, we discuss SCADA and HMI, and we discuss safety system. So you can imagine someone going through the foundation class being able to do SIL calculation, understanding low power, and all of those things. We broke everything down. Presently, their project is on PID algorithm. They are learning how to tune a simple process. So once they are done, we'll flaunt their results in your faces so that you will see that the class is very, very useful. And I mean, I don't want to overstate it, but it's highly recommended. Elijah.
All right, sir. Thank you very much. Good morning, sir. So I just want to I don't know, it's a minor complaint though on skill catalyst. So I think anybody from the Federal University of Technology are correct. I don't think their email will be registered as a student on skill catalyst. Like it's not accepting our email.
Really?
Yes, sir.
Okay, if you're on the WhatsApp group, just drop it there and we'll resolve it.
All right, sir.
Yeah. All right, everyone. Thank you very much and have a beautiful weekend.
Thank you, sir. God bless you, sir. Thank you.